going to start recording now because it's all good new stuff. So, capital W for work, it's actually the change in energy. It is not energy, it's the change. Whether it's gaining or losing, you're increasing your energy or decreasing your energy. Whenever there's a delta, we can say it is final minus initial. The equation is F times S. Okay? So work has units of newtons times meters. If you want to be cocky, you could express your units in Newton meters, or you could call it a joule. Okay? So if we were to multiply a Newton by one extra unit of meters, then we would get kilogram. Let's go my blue kilogram meters per second squared times by another meter. 1 joule is a kilogram meter squared per second squared. All right, there are lots of different arbitrary definitions of a joule. It's the potential energy that a 100-gram object gains as it is raised a height of 1 meter, approximately, a joule. Or a 1 kilogram object travelling at, a half a kilogram object travelling at 2 meters per second. I mean, or if a 1 Newton meter is allowed to act over if 1 Newton of force is allowed to act over 1 meter. So let's just say that the force required to push this hole punch is a Newton. If I push this hole punch 1 meter, I have just done 1 joule of work. I have transferred 1 joule out of my body. I am now less by 1 joule. I did 1 joule of work. My delta E, -1. This ties in with conservation of energy. I didn't destroy the energy, I transferred it. So if I lost 1 joule of energy, something else must have gained it. Okay? Well, look at this hole punch here. It doesn't have any kinetic energy. It doesn't have any potential energy. Where did that energy go? Let me do it again. 1 joule. There. Friction and
noise. Sound.
Friction and sound. Okay? I got it moving, but then it lost it. So there's a lot of philosophical things that we can look at as to where the energy's gone. Is it useful? Does the object still have it? We've made heat. Can we get any of that energy back? So it leads into all thermodynamics and efficiencies and things like that. Yes, Emil?
Which of these are vectors?
Ah, very good question.
Newtons are...
No, good point. Work, even though force and displacement are vectors, work is scalar. It doesn't have a direction. All right? It loses its direction because in the example of heat, all of those particles now we would say are jiggling erratically. It's scalar. So make a note of that if you want. Work is scalar, energy is scalar. It does not have any direction. Okay? I tell this to my year 7s, 8s, 9s and 10s. Energy is weird. You can't point at something and say, there's energy. It's a property that objects have due to their state or their position in space. The definition involves work, and then if you go to work, work also has a definition. It's the transfer of energy.
So there.
So yeah, you get stuck.
Cyclical.
So work is the transfer of the ability to do work.
Yeah. So you get stuck in this definition loop. So boys, to get out of this to get out of this definition loop, you say the ability to cause change. And the ability is important. It's just basically covering the potential energy side of things. So it doesn't have to be active energy. It could have the potential to become active. All of the objects on my desk right now have the potential to transfer that energy. All right, I could push them all off the table and they would go careening into the ground. They would convert their potential energy into kinetic energy. Okay? Now, what just happened to my screen? Thank you for just shooting off at any random point. Come on, little laptop. Thank you. Thank you. All right. The force must act over a distance. Have a look. I draw this diagram all the time. Imagine I walked up to a wall, right, and I applied from my... No, let's put my arms up here. I applied 1,000 newtons. All right?
God, that's a good diagram.
Thank you.
That's a lot.
Now, here's the thing. I could be pushing against the wall. We could do that. You could get a set of bathroom scales. You push against the wall until it reads 100 kilos. You're now pretty much applying 1,000 newtons. But it's not acting over any distance. There's no S, you know, S equals 0. The wall doesn't move, okay? In that case, there is no work done. There is no transfer of energy to the wall. That's the important thing. I might be doing work, all right? I could sit there for a half hour applying this 1,000 Newton force. I would start sweating and panting and I would start overheating. I'm transferring chemical potential into heat inside me, but I'm not transferring it to the wall. So you've got to be careful when you hear the word when you hear the word work, you could replace it with transfer of energy, and then that implies a direction. So I can either do work by losing energy, or work can be done on me. I could gain energy. So when I eat an apple, work is being done on me. If I'm in an elevator and I'm going upwards, you would say work is being done on me. I'm gaining energy. My delta E is positive rather than being negative. Okay, you've got to be careful when you look at the transfer, because sometimes out will pop a negative force or a positive force. Have a think. If your work is negative, then your F must be negative. That will oppose. If work is positive, then F must be positive. Think of accelerating a car, then F would be positive. If you're decelerating a car, F would be negative. In both those terms, in both those scenarios, work was done. In one, work was done on the car, and in the other, the car did work on its environment. Okay, so
direction.
but don't think vector. Think flow of energy into or out of the object.
If we write an answer, we have to write like 680 newtons.
Well, you wouldn't go positive or negative. You would use the correct terminology. Let's use an example over the page. Let's suppose I wanted to lift an object up. The object has a weight of 100 newtons. If I wanted to rise that object upwards, the average force over a metre would be 100 newtons. We'll speak about at the start and at the finish in just a moment. The average force would be 100 newtons up. We would say that the work done on the mass is going to be delta E, which is going to be F times S. We'll say 100 times 2, 200 joules. It gains energy. Okay? So let's just add what Sam was asking before. You can make these kind of statements. If your final energy is greater than your initial, then you're going to have a positive work value, right? If you're gaining energy, you would say work has been done on the system. Pretty much. So, and in this case, the system is pretty much the box, all right? We're not going to make it too complicated. There's not going to be 3 objects tied with strings. It's just the object, work was done on the object, all right?
So
it gained energy. If it was the opposite way, let's now have this object slide down a ramp and then come to rest in the ground. Well, in that case, its final energy would be less than the initial. You would have a negative work value, and you would say work has been done by the system. All right, so important terms. And just be careful if you're ever asked to make statements, you need to make sure you're using the right words, because they're going to imply which way the energy's flowing, whether it's gaining or losing. Now, most times when I say to students, you have to apply 100 Newton force to raise this object up, most of the CLUE students go, well, hang on, wouldn't you need to apply a little bit more than 100 newtons at the start to accelerate it? And then constant speed would be 100, and then a little bit less to decelerate it. And I would say, you're absolutely correct. On average, however, it would be 100 newtons. Let's just draw this. The force that you would have to apply over the 2 meters, okay? As I said, a little bit more. Oops, let me try this again. A little bit more, and then a constant 100, and then a little bit less, and then 100. And then 100 to keep it there. Imagine you're holding it up there with your hand and it's now stationary. Well, you're still holding that. On average, it would be 100. And really, that area there should fill this area here, if I could get a smaller highlighter.
Is that when it's like accelerating at us?
Yeah, so let's label that. That would be accelerating. This would be constant speed. And then this, well, that should be a T. And then this would be decelerating. Okay. Now, we've just brought an interesting concept in. F times S is area under this curve. So work is the area under the curve. As mentioned before, do not confuse, the last week we had a force time graph, that would be F delta T, that's impulse, change in momentum. The area under this curve is going to be the work done. Okay? So just remember that. And as we know, you're not always going to get nice functions, but if you're lucky, it'll just be a square or a rectangle or a triangle. Have a think in the past. Let's think back to Altair, who jumped into the bale of hay. We would look at the force as a function of time.
What?
And
Who's Altair?
you were not here.
Oh.
So just sit quietly, smile and nod like you know what I'm talking about. Person jumps into a bale of hay and they hit the hay with a certain speed and then they come to rest. There's an impulse. It caused their momentum to change. We would have said that the impulse was the area under an F delta T graph. Well, now, instead of looking at how long it took for them to come to rest, we could go back to that scenario and go, how far did he travel before coming to rest? If we could then get a force distance graph, I think we said that the hay was compressed by 1 metre. Well, now we could do a whole new scenario, go, he came in with all this energy, kinetic energy, a half mv squared. And that half mv squared had to be removed by an opposing force over 1 metre. Well, that would be the average force, remember? Because you're going to get a big spike. But on average, we could go, that was the average force that acted over a metre to do work, the work done by Altair, because he lost the energy, would have removed all of that. Okay.
Would the work you would be doing?
We'll look at some. We'll look at that in due course. Now, sometimes you need to find the parallel force because it turns out it's only the component of the force that acts in that direction. So let's just add here. This is going to be F parallel to S. Okay. So it's only the component of the force that is in the direction of the displacement that does any useful work. This downwards component, well, that's just going to push the object into the ground, which might, you know, if we could look at what happens, it might increase the normal force, but we don't really care. Think about lifting an object upwards. As you're pulling an object along, it's not that's not doing any useful work. All right, so I'll just add here F perpendicular is not doing work. It's not transferring energy. Again, those two terms are completely interchangeable. So the work done, or the energy transferred, we could write here is work equals, write the whole logic out, so write the whole damn thing. Delta E equals E final minus E initial equals F times S. The work done, or the energy transferred to the box, in this case, is going to be F cos theta times S. Okay? And that would make sense. To get the most work done, you would want to have your force in the direction that you're pushing it. That makes, hopefully, logical sense. If you stood there pushing the object down into the floor and wondering why it's not moving left, it's because you haven't got any parallel component. If you want the most parallel component, you want to push in the direction that the object's moving. Okay. We'll ignore friction for now. I could have put this thing on wheels. It would have made it a little bit more sense. Let's get over the page. This question I've pinched from an old Christchurch test paper from, I don't know, 5 or 6 years ago. There's a husky that is pulling a sled, and we're just going to assume that he is applying a downwards force through the lead. Okay? In which case, we require F parallel. And turns out, by given the dimensions here, you could just say cosine theta equals adjacent. No, we'd have to do some tangent, actually. The theta, quick little side mission, is 16.7 degrees. Okay? The husky in the diagram pulls this sled along a horizontal displacement of 17 by 10 to the 3 meters, and we've been given the tension. Let's find out the work that the husky has done. So we'll go, and I'll just put in my little symbol now, F parallel. So we have to do that side mission. We'll go 360 cosine 16.7. I saw your hand go up and I ignored it. So the work done by this dog, applying that parallel force over that horizontal distance, 5.87.
It's the
tension in the lead.
F equal to T.
Put your hand up if you have a question. Why can I not draw an 8 today? 5.87, 10 to the 6 joules. Now you've got to be careful there. There's no question here, but the question would have to say, calculate the work done on the sled. That's plus 587 by 10 to the 6. The work done by the dog, negative 5876. That energy has been removed from his body, but maybe the sled is going at a constant speed. This is another interesting sort of philosophical conversation. If the sled is travelling at a constant speed, Manus, is any work being done on the sled?
Yeah. Overcoming friction.
On the sled. Is the sled gaining or losing energy if it's travelling at a constant speed on a horizontal surface? No. So why is this dog putting in all of this energy if the car is not gaining any speed and is not rising up any vertical height? Where is all that energy going? Friction. Pushing snow out of the way and creating friction and melting snow. So it's all wasted at the end of the day. This is the sad story of the universe and thermodynamics, is that all of that energy is eventually just going to turn into heat. Right? Eventually the cart's going to stop. The husky then says, I've had enough. The sled just doesn't continue sliding on for infinity at 10 meters per second. It's going to go and stop. This poor husky has just wasted all of that energy. Well, maybe it was important that the sled travel 17 kilometers, so you could say, we got some good thing out of it. But in terms of energy, it's all gone. So, again, be careful on the wording. And I believe I have an example. Pushing the prowler sled up in the gym is a good example, and I hope I've got this example over the page. No. Maybe. Let's keep going. Actually, no, let's go back to the husky. For some strange reason, I just added a useless fact here, that if you divide this number by 4,180, you get the number of calories that the husky would have burnt, and that would have been 1,400 kilocalories. So that husky would have to then munch down on some chow to make sure that he gets all of that, because if...
Too many calories,
17 kilometres, Sam. This isn't just a couple of laps around the oval.
I've always wondered.
This husky's like crossing a lap.
That's like...
These numbers, by the way, have all been made up, alright? I was just making these numbers up.
I wonder, can I just ask, is like, if you like... if one person runs 100 metres, say, is that always the same amount of calories burnt, depending on...
It's muscle mass. Muscle mass.
Well, that's accounted for by your work, right? So when you get that reading of like how many calories you burn on an exercise bike or an that's not true.
It's the amount of energy you're basically converting energy into calories. So you divide by 4,180, which the calorie came from the energy required to raise a kilogram of water by 1 degree.
And is that the same calories you're talking about when you're talking about like caloric surplus and deficit? And like, so like
Eating calories and expending calories.
So like if you eat a donut 100 calories,
Yep.
and then you do 100 calories on the exercise bike,
Energy in, energy out.
Is that like facts? Like
Yep.
it's-
So as I was about to say, have a listen, gentlemen. Shh. Have a listen, gentlemen. Your husky requires a fuel source, and if it's not eating 1,400 calories, Manus, if it doesn't eat 1,400 calories, it will.
that a kilocalorie is what people talk about.
1,400, Manus, listen.
1.4 million calories.
If it doesn't consume those calories, then the husky's body will look for that energy source in other areas. It'll convert fat into energy.
Yeah.
It can convert muscle into simple sugars by gluconeogenesis. If you want your husky to stay at the same weight, you make sure that calories in equals calories out. If you want your husky to gain weight, you've got to put more calories in, and it will create mass. It will either make muscle or fat. That's about all that you'll make. All right, so if you have a husky sled of dogs, and you need to make sure that you're feeding them the correct amount, because if you're not feeding them enough, your huskies are going to muscle atrophy. They're going to lose mass. They're going to not be as strong. Okay, let's get to these. I like to very quickly show you the equations that are in your data sheet. What?
We always have to write work is equal to
Yes.
EF minus
Yes.
ER is equal
Yes.
to work equals change
Yes.
always.
Always.
Even in a text.
Correct. I'm glad we had this conversation.
Will we lose marks if we don't?
Yes.
Is that a lie?
No.
Right, so start writing W-E.
All right. Now, guys, we know the equation for potential energy, but I just want to show you its origins here. If you lifted up an object a certain height, we would be saying you would need to apply a force equal and opposite to its weight force. So, on average, you would have to apply a force upwards that was equal to its weight in magnitude. All right? Then we're going to move at a certain height. Now, we could call this delta H, which is H final minus H initial. Okay? Now, that turns out that this force is going to be mg, and the S term is going to be delta H. Remember, it's a change in. We want that delta, should really have been here, delta S, force acting over a difference in displacement. Just hold on. It's scalar, it's double negative, it doesn't matter. We don't have negative energy in this case. So let's just rewrite this as the change in energy could be written as mg delta H. Let's just expand that energy is final minus initial, which is mg H final minus H initial. So maybe we could attach that the final energy is mg H final, and the initial energy could be paired up with the initial term. So we could say it's mg H final minus mg H initial. This is what's actually happening. The delta E of that object depends on where it started and where it finished. Now, if I took this hole punch, right, have a look. I pick it up off the ground. I place it on the table, right? I said it raised by 1 meter. It now has 10 joules of potential energy. I didn't care that we're actually 4 meters off the ground right now, so I could have said I lifted it from 4 meters high to 5 meters high. Doesn't matter. 5 take 4 is 1. So you don't care where you are. I neglected to tell you that we're actually about 15 meters above sea level, so maybe we could say I went from 15 meters to 16 meters. Doesn't matter.
Still one.
Let's just set delta H as 1.
As long as you
The other easy way to get around this is to just set H initial as 0. If you set H initial to 0, then it's just how far did it move in this scenario. And a lot of people do. In questions, in your data sheet, we have potential energy equals mgh. All right? So if a question says a 1 kilogram mass is lifted from 5 meters off the ground to 6 meters off the ground, then you just have to say h must be 6 take 5, h equals 1. All right? You don't have to go, oh, it went from 565 to 772 and the difference between those. You could if you wanted to, but the end of it is by how much energy did it receive or lose. All right, so that's the first derivation of the equation that all kids need to know in year 8, 9 and 10. Let's look at the next one. This one's fun. If we have an applied force that acts over a distance, let's say that we have a certain initial speed. We could set it equal to 0, but for this I'm going to make it non-zero. And then it's going to have a certain final speed. Okay? The force acts on a certain mass. Well, let's do a few things. Let's go back to our SUVAT. We could say that v squared would equal u squared plus 2as. And so the acceleration could be rewritten as v squared take u squared over 2a. I could then throw this into my sum of all forces. 2s, thank you. The sum of all forces is going to be the applied force, because we're not worrying about friction right now. And that's going to be equal to ma from Newton's second law. Let's throw in a. So that's going to be m outside of v squared take u squared over 2s. Okay. We now say, well, maybe the work done is going to be Fa times s. So I'm going to take that whole term and I'm going to multiply it by another s term. So that's m outside of v squared take u squared over 2s times s. Cancely. We get an expression that work done, I'm going to write it as E final minus E initial equals, now I've got a v squared and a u squared. Let's expand this out. I could say, well, that's mv squared on 2 subtract mu squared on 2. All right, now have a look. I've got a final term that corresponds to a final velocity. I've got an initial energy term that corresponds to an initial velocity. So I can now get an expression for an energy as a function of any speed is just going to be a half mv squared. To make things easier, we could have just said if the object started off stationary, if I set u equal to 0, then that equals 0, that equals 0, the final energy is just a half mv squared. Okay? Now, you can see, gentlemen, that this has come straight from SUVAT, but we're at a platform now where I want you to go, work is F times S, which will create a half mv squared. You do not need to show this derivation. If you are asked to show using concepts of work and energy, you would be going like that. Right? You could also write it as a half mv squared minus a half nu squared. Okay? So, by the way, let me get to the final statement. Your kinetic energy equation is simply a half mv squared. That's in your data sheet. You need to have your mass in kilograms and your speed in meters per second. Again, it's not it's a scalar. Let's just check my friend dimensional analysis. Kilograms multiplied by meters per second squared is kilogram meters squared per second squared, which we said was the derived unit of the joule. Okay? Yo.
So if we did like in year 7 and 8, we did a bunch of questions about like kinetic energy and calculating kinetic energy. If it didn't start at rest, you'd have to use the first.
Yeah, if it didn't start at rest. So this is, we could do it, and there might be questions. A car is cruising along Stirling Highway at 10 meters per second. It steps on the accelerator. An applied force acts over 50 meters. How fast is it now traveling? Do you mind if I just go off on a tangent and do that? Sorry guys, find some space if you want. Let's just do that. We've got a 1,000 kilogram car at 10 meters per second, cruising along, dawdling along Stirling Highway at that speed. It then applies, we're going to ignore friction, it applies a force of 2,000 newtons over a distance of 30 meters. So it steps on the gas, and it travels 30 meters with this extra force. The question might be, what is its final speed? Now, we could do SUVAT. We could go find the acceleration, v squared equals u squared. But if we had to do concepts of work, we would say final minus initial equals F times S. The unknown would be hidden somewhere in here. Another way to look at this is that your final energy is your initial...
You forgot delta E.
Yeah, sorry, delta E. You could also write this as that your final energy is your initial plus any work that's been done. Right? Now that work could be positive. Have a think. If this term is, this is what we said before, if work is positive, then your final would be greater because we're adding a value. Well, what are we adding? We're adding 60,000 joules. That's what that's saying. I'm going to add 60,000 joules to this car. It started off with a certain amount of joules, add 60. What's it got now? Well, what it started with plus 60,000 joules. Let's do it. Let's go E final equals... I'll do it in steps. There's obviously different pathways that you can take. Correct. What was it? It was F was 2,000 times 30. Was it? 2,000. 2,000 times. Yes. Well, let's just go 10,000 times 100 would be 1,000,000.
It's 50,000.
5,000 times 100 is 500,000.
It's 50,000.
Oh, sorry, 50,000 plus 60,000. That's the final energy. Well, okay, now that's going to be EF equals a half mv squared, which equals now 110,000 joules. We would then need to rearrange for V. So you're going to times both sides by 2, divide by m, and then take the square root. I'm doing all of this in one step. I hope you don't mind. Little side mission. V equals the square root of 2ek on m. I'm expecting all of you should be able to rearrange your kinetic energy equation to solve for V and m.
Shouldn't it technically be plus or minus?
Cancel, 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 cancel. It's going to be equal to the square root of 220. If somebody wouldn't mind telling me what that is.
14.8.
Thank you. So, we've now figured out that the car accelerated from 10 to 14.8. Homework activity. You could do this same question using SUVAT. Remember what I said last week, or the week prior. You're going to be doing exactly the same mathematical operations, but just in different orders and calling them different things. All right? So if you look at what we did here, I mean, there's a lot of maths going on, right? But we did it in a certain order, and we said, oh, that's change in energy, force times displacement. Right? If you looked at this using SUVAT, you would go, well, let's find the acceleration. Let's find the acceleration, F divided by m, and then v squared take u squared. It's all there. It's just called something different. So just be careful. You could be tested on your ability to do either at any stage. In the exam, there could be a question, and it would say, calculate using the concepts of rectilinear accelerated motion, SUVAT. All right, I've been speaking for too long. Have a go of this question. I'll give you a hint. There's different ways to solve this. You could just look at its vertical height, or you could look at the force acting along.
There's no question, sir.
Yes, there is.
No, there isn't. Calculate potential energy. All right, you go. Calculate EP, the potential energy. All the work done. Okay, you got two options. Work or potential energy. Turns out it's going to be the same answer. Okay, have a go. And again, we'll go that we'll start at 0 and we'll get to a H final. Okay. Just keep working, Cameron. Don't worry about them. They're coming out of their PAT testing.
Interesting.
So yeah, I'll give you a hint. There's two different approaches to this question, and I want to see which approach you've gone by. All right, we've got 2 minutes left. I'm just going to split it down the middle. Has somebody got an answer?
Yep.
Cameron, what's your answer?
Times 4.
134. Okay. Cameron, did you go MGH or force times distance? Okay, perfect. All right, cool. So, Cameron's just told me here's what he did. All right, so I want to know if you did this as well. Cameron said that F parallel is mg sine theta. So that's the force that acted along 4 meters. So Cameron looked at work equals F parallel times S, which is change in energy, which produces your potential. So we'll go 10 by 9.8 sine 20 multiplied by 4 gives 134 joules of work done. Okay?
I did 2 steps. It's easier way.
So how does the parallel times come out as?
Mg sine theta, that's the force up the incline.
Right, but
From a forces on an incline, mg sine theta is down, he's got to apply that
the
upwards.
force to get it up there is also the force that it will have at the top.
Well, an average force, to get it from there to there, an average force must be mg sine theta. A little bit more at the start to accelerate it, a little bit less at the end to decelerate it, but on average. Okay,
No, I guess
did anyone do a different method?
yeah, it's MGH.
What did you, okay, so how did you find H final?
H is equal to 4 sine 20.
So you did 4 sine 20, and so your E potential equals mg s sine 20. All right. So we'll go 10 by 9.8 by 4 sine 20. I didn't even calculate what it was. It's probably 3 or 2 or something.
It's the exact same thing.
It's 1.3.
134 joules. So here's an interesting thing, gentlemen, to end on. Doesn't matter which one we did, we still had to reduce something by sine 20. You either reduce the force of the weights by sine 20 to get the force on the hypotenuse, or you reduce the hypotenuse by sine 20 to get the vertical distance. Right? So again, either approach is still using concepts of work and energy. You can't really solve this using SUVAT because it's a constant speed. Or we're not caring about kinetic energy. The next, here's a wonderful extension question for you.
No.
What would the minimum force be to get this travelling at a constant speed? Right, mg sine theta. Could somebody just quickly tell me what 98 sine 20 is? Could somebody tell me? 34. 34 newtons would get that sucker travelling up at a constant speed. How fast would it be travelling at the end if I applied 40 newtons?
Forget on that.
The answer might surprise you.
33.5.
Thank you, Michael.
Alright, so now we would say work equals F times S. That's now going to be mg h final plus a half mv squared. We've got 2 types of energy going on here. So,
Oh, yeah.
So,
lots of fun questions.
you can do that.
See you later, guys.
Force parallel times displacement.
Because on this scenario,